Welcome to the next lecture in electrical machines. We were discussing the synchronous machine, and in this particular lecture we are going to cover what is voltage regulation. So voltage regulation is defined as the rise in voltage when the full load is removed, keeping the field current and speed the same, and it is divided by the rated terminal voltage. So in terms of mathematical derivation, the voltage regulation is defined as the difference between the no load voltage and the full load voltage ratio to the full load voltage multiplied by 100 to convert it into percentage. The magnitude of the change in the voltage depends not only on the load but also depends on the load power factor. So we have discussed this in the previous lecture, the effect of armature reaction. So here the voltage basically changes when there is a change in the load, and the power factor also plays a very important role in the voltage drop. So here we can see the graph between the terminal voltage and the load current. The power factor, when it is unity, it is just constant, which is parallel to the x-axis. But when it is lagging power factor, then there is a drop in the voltage, and when there is a leading power factor, then there is a increase in the terminal voltage. So the voltage will change with the change in the load and the change in the power factor. So the topic for today is to determine the voltage regulation by different methods. So what are the methods that we use to determine the voltage regulation? So for any small machine, we will go by direct method of loading and try to find the voltage regulation as the change in the voltage between the terminal from the no load condition to the full load condition by full load condition. However, for large machine, direct loading is not justified, and hence we have to go by the indirect method of testing the machine. So the direct method, first we will take. In the direct method, alternator is driven at the synchronous speed and voltage is adjusted to the rated value. So this voltage of the alternator is kept at the rated value, and the alternator rotor is driven at the synchronous speed. Then we vary the load until the wattmeter and the ammeter indicates the rated values at a desired power factor. So the reading of the wattmeter and the ammeter should indicate the rated values. So these rated values will be available on the nameplate details of an alternator. Now we will throw the entire load of keeping the speed and the field current constant. So two parameters we have to keep constant, that is the speed and the field current, and the entire load is taken away from the machine. Then the open circuit or the no load voltage, which is denoted by E0, is read, and then the voltage regulation is found out using the formula, which is E0, that is the no load voltage, minus V, that is the full load rated voltage, divided by the rated voltage multiplied with 100. So here in the direct method we can see that first the machine is brought into the rated values, and then suddenly the load is being taken off and the reading of the no load voltage is taken. This voltage V is already given in the nameplate rating of the machine. So this is the direct method, which is done for the small machines. Large machines, the cost to find the regulation by direct loading becomes prohibitive. So when the size of the machine become larger, we no longer stick to the direct method and we have to move to the indirect method, because the cost involved in finding the regulation is very high. So next we'll discuss what are the indirect methods available to find the voltage regulation. The first method we will discuss under the indirect method is the synchronous impedance or EMF method. Second method is known as the Ampere-Turn or the MMF method. Third method is known as the zero power factor method or the Potier method. So these three methods we will discuss under the indirect method of finding the voltage regulation. Now all these three methods of determining the voltage regulation will require certain aspects. So it will require to measure the armature resistance of the machine. These armature resistance will be measured directly using the voltmeter ammeter method or the Wheatstone bridge method, because we have to measure the resistance of the armature, so we can go by any one of the direct measurement methods. Next we required open circuit or the no load characteristic of the machine. So keeping the circuit open, we have to measure the relationship between the voltage and the current. This is known as the no load characteristic. Now for the zero power factor lagging condition for the Potier method, we require the short circuit characteristic as well. So basically three different methods we require, which are required to find these three different indirect methods. So this testing, that is the armature resistance testing, open circuit or the no load characteristic, and the short circuit characteristic would be required to find the synchronous impedance, Ampere-Turn, and the zero power factor method of calculating the voltage regulation. So the open circuit test and the short circuit test on the alternator is very simple. In the open circuit test, we keep the terminals open. So we do not connect anything on the terminal. So this is open. Whereas the terminals of the under the short circuit test, we will keep it in the short circuit position. So the phenomena goes like this, that the machine has to run at the rated speed both for the open circuit test and the short circuit test, and we have to measure the field current. So the field current we have to measure, and we have to measure the relationship between the field current and the open circuit voltage. Similarly, we have to measure the field current versus the short circuit current. So here we are going to measure the voltage for the open circuit test, and for the short circuit test we are going to measure the current, that is the armature current. So if we see the graph of the open circuit characteristic, so it will go in the straight line and then slowly it will saturate. So this point is due to the saturation, where even we increase the current, the voltage remains the same. So in the short circuit characteristic, there is a straight line which is on increase in the field current, the armature current will increase. So these two testing will be required for determining the voltage regulation. Now the first method of determining the voltage regulation is the synchronous impedance or the EMF method. So in the synchronous impedance or the EMF method, we have to draw the graph and the measurement of the OCC test, that is the open circuit test, and the short circuit test. So two tests we are going to do, and we have to keep the two things constant, that is the synchronous speed of the machine ns, and we have to keep the field current. So these two parameters we have to keep it constant. So for a particular field current, we have to obtain what is the value of the no open circuit characteristic or the no load voltage. Similarly, for a particular amount of the field current, what is the value of the short circuit current? Then we can write the synchronous impedance of the system or the alternator is the ratio between the open circuit voltage by the short circuit current. And in terms of the circuit parameters, we know that the ZS, that is the synchronous impedance, is equal to under root of the armature resistance square plus the synchronous reactance square. Now we can find the synchronous reactance of the machine directly when we have obtained ZS and we have already measured RA using the voltmeter ammeter method or the Wheatstone bridge method. So here XS we can find as the ratio under root of ZS square minus RA square. Now we can draw the phasor diagram of the voltage, current and the different drops. So if we take the current as the reference quantity, then the current is lagging behind the voltage. So this can be a lagging power factor condition where the drops we have IRA is the drop across the resistance and IXS is the drop across the synchronous reactance. So the no load voltage E naught can be calculated from the formulas obtained from the phasor diagram. So the no load voltage is under root of V cos phi plus IRA square plus V sin phi IXS square. Once we have calculated the value of E naught, we can find the voltage regulation using the formula E naught minus V by V into 100. So this will give us the voltage regulation. So our main motive is to find out the no load voltage when the load is thrown off. So here we can see that we have not put any load on the machine. So this is known as the indirect method of finding the voltage regulation. Now we understood that it is basically a pessimistic method of finding the voltage regulation. So what is the meaning of pessimistic method? That it is not very accurate. So pessimistic method is not very accurate. The ZS that we have found out is greater than its value at the normal voltage condition and saturation. Since ZS is more than what its accurate value, the XS is also not very accurate and E naught is also not very accurate. So the EMF method is not very accurate, but it is the simplest method of finding the voltage regulation. So here we have to note that we have tried to find the value of XS, and in the previous lecture we have discussed that there is known as leakage reactance and we have something called armature reaction. So these together make to be XS. So here XA has not been treated separately. That is, the armature reaction effect of the reactance is not treated separately, but it has been taken along with XL. So two limitations we have here. This is the first limitation and this is the second limitations of the EMF method. With the pessimistic method, not accurate because the impedance found is more than the value for which it is the accurate value. Second, the armature reaction is not treated separately, but it is taken along with the leakage reactance of the machine. So these two limitations are there. However, the EMF method is the simple method of finding the voltage regulation. Next method that we are going to discuss is basically the Ampere-Turn or the MMF method. So it is the converse or the opposite of the EMF method because the leakage reactance is treated as an additional of the armature reaction. So this limitation of the EMF method is taken into account here, that the leakage reactance is treated as an additional of the armature reaction. Then the field Ampere-Turn required for the voltage on the full load condition is the vector sum of the two quantities. One is coming from the OC test. So OC test will give the field Ampere-Turn required for the voltage, or if RA is to be taken into account, then V plus I RA cos phi on no load condition. So here under the no load condition, which is the open circuit test, we get the field current required for the voltage, that is V plus IRA cos phi. And other from the short circuit test, field Ampere-Turn to overcome the demagnetizing effect of armature reaction on the full load current is there. Field Ampere-Turn required to produce the field load current on short circuit will balance the armature reaction and the impedance drop. So the field Ampere-Turn, that is the MMF, will be required to produce the field current on the short circuit, and it will balance the effect of the armature reaction and the impedance drop. So two things it will balance. So here ZS drop is neglected because armature resistance is very small. So since armature resistance is very small and excess is also small under the short circuit condition, we will drop the ZS drop is neglected. Power factor on the short circuit is almost zero lagging, and the field ampere turns are used entirely to overcome the armature reaction, which is wholly demagnetizing in nature. Then if we have to draw the OCC characteristic of the machine and SCC characteristic of the machine similar to the EMF method, and little bit difference is there where we have to obtain the phasor diagram to find the value of E naught. So first we have to do that the OA, so this part OA, which will represent the field current for the rated voltage. So here, since we know that this x-axis is basically the field current, so OA represent the field current for the rated voltage. Then the OC will represent the field current required to produce the full load current on the short circuit condition. So here we see this OC will represent what amount of the field current is required to produce the short circuit condition. So here that is the reason we have taking and intersecting this with the OCC characteristic, and OC we are intersecting with the short circuit characteristic of the machine. So that represent the various full load current of the machine. Now the AB vector is equal to the OC vector. So here we have to draw a vector AB which is equal to the OC vector. So these OC length and AB length are same, which is drawn at 90 plus phi degree. So this is 90 plus phi, which is phi is the power factor to OA, where power factor is lagging. So phi basically coming from the power factor of the machine. So we have to draw AB is equal to OC. Then the total field current is basically OB. So we can see from here that this is the total field current OB, for which the corresponding OC voltage is E naught. So once we can drop it here on the x-axis, and we can find out what is the value of the voltage E naught, that is the no load voltage. So this is the total field current of the machine that will produce the no load voltage E naught. Now this is the optimistic method, and it is the converse of the EMF method. It give result less than the actual value. So it will be giving you less value than the actual. In the EMF method we were getting the pessimistic, we were getting more value than the actual value. So both the methods EMF and MMF are not giving the accurate values of the value of E naught. So E naught being the no load voltage of the machine, after calculating we can easily find the voltage regulation as E naught minus V by V into 100. So this is the voltage regulation of the machine. So the third method that we are going to discuss is basically the zero power factor method, or the Potier method of finding the voltage regulation. So here in this method, it is based on separation of the armature leakage reactance drop and armature reaction effect. We have seen that in the EMF method, armature reaction was taken precisely in the Excel. Excel, that is a leakage reactance. Here, and the MMF method, we have taken it along with the XA. Here, we will taking both as separately to find the zero power factor method. So it is basically giving more accurate results. So compared to the EMF method and the MMF method, our zero power factor method will give you the accurate result. So it will make use of the first two methods. So it is basically the combination of the EMF method plus MMF method to find the voltage regulation of the machine. So first we will draw the OCC characteristic and the full load zero power factor, not the SSC. So we are not going to do the SSC, but full load zero power factor we are going to draw. So zero power factor curve is basically the voltage against the field current when delivering the armature current at zero power factor under the full load condition. So this is the definition of zero power factor curve. We are basically drawing a curve between the voltage, terminal voltage, and the field current when the armature current under the full load condition is at zero power factor condition. So we note that the value of E naught, that is the no load voltage, is basically terminal voltage V plus the drop, this is the total drop IA RA into plus J times XL, plus we have the armature reaction drop, assuming the lagging power factor condition. So this is the full voltage regulation, full voltage formula, no load formula, when different drops are taken into account. Now, how do we obtain the Potier triangle and determine the voltage regulation that we are going to see? So first we are going to draw the curve of the zero power factor full load curve. So this is the zero power factor full load curve. So we have to draw this, and we have to draw the OCC characteristic of the machine, which is the no load curve of the machine. So this is the no load curve of the machine. And then this is on the x-axis we have the field current, and on the y-axis we will be getting the value of the EMF E. How to find the Potier triangle and how to find the voltage regulation, that we are going to see. So first, point B is the reading where wattmeter reading is 0. So we can see that in the point B is where, first we will denote the point B where the wattmeter reading is 0, no reading is coming, and point A is basically the short circuit test with the full load armature current. So here the value of A, that is OA, is basically the short circuit test which is giving you the full load armature current. So these points we will be marking on the curve. Then OA represents the full load current, where OA represents the current, full load field current, and in opposite to the demagnetizing armature reaction for balancing the XL drop at the full load. So here this OA, what is the field current corresponding to the OA? That is, it is opposite to the demagnetizing armature reaction, and it is balancing the leakage drop at the full load condition. Then from B you draw a BH which is equal and parallel to OA. So this is your point B and this is your point H. So we are drawing a line BH which is equal and parallel to OA. So our distance OA is here. So these two lines are equal and parallel. Next, from H, so this point H we have obtained. From H, we draw parallel initial straight line to the no load curve. That is parallel to the OC curve. So OC we have to first obtain. So here we have, so here O and C, which is the line which is parallel to the OCC curve, So we have from H, we have to draw a line HD which is parallel to the OC curve. The OC curves lies in the open circuit characteristic of the machine. We get a point D on the no load curve. So this point when we draw it, so it intersect in the OCC curve. So this is our OCC curve. So it is intersecting at the OCC curve which correspond to the point B on the full load ZPF curve. So this point which is intersecting at the point D which correspond to the point B on the full load ZPF curve. Triangle BHD is basically the Potier triangle. So this triangle is basically the Potier triangle. Once we have obtained the point B, we can intersect with the OCC curve and find the value of the E0. So this will give you the voltage regulation equal to E0 minus V by V into 100. So this is the voltage regulation of the machine. Then at this point we draw a DE which is perpendicular to BH. So we are drawing DE which is perpendicular to BH. Then DE represent the drop due to the leakage reactance. So this IXL is basically the drop that is due to the leakage reactance of the machine. And BE, that is the point B here, and we have the point E on the machine. This is BE. This is the field current to overcome the demagnetizing effect of the armature reaction and the full load condition. And EH for balancing the XL drop DE. So EH will be there, which is balancing the leakage reactance drop DE. Then the E is basically equal to DF. So we can have the point D here and the point F here. If we intersect this point DF is basically the total EMF E, which is equal to V plus I times JXL, because we have neglected the value of armature resistance, and IF is equal to OF. So the field current IF corresponding to the OF of the vector diagram here, we are getting the value of E, and we have neglected the armature resistance of the machine here. And the NA, that is the point, if we see, this is the point N and this is the point A, which is equal to the point B and E, because we have obtained BE. So this NA and BE are equal, which represents the field current needed to overcome the armature reaction. So we can see from this vector diagram and from this method that Potier method is taking all the effect of the armature reaction. Then the sum of the vector NA plus OF. So sum of the vector NA plus OF. So O is here and F is here. Sum of these points will give you the field current for E0, read from the no load curve, where NA is equal to FG. So here NA and FG points are equal, similar to what we have seen in the MMF method. So we can obtain the no load voltage using the Potier method. So in this particular lecture we have discussed three different methods: EMF, MMF and Potier method, to obtain the voltage regulation of the machine, and that are for the indirect methods for the large machine, and for the small machine we will go for the direct methods of finding the voltage regulation. So thank you for now. See you in the next lecture.